Have you ever held a basketball underwater, or any kind of ball? You feel an upward force on that ball. It wants to come to the surface. Why is that? Well, we talked about before the fact that if an object has a net mass density that's less than water, then it'll want to float. If it has a net density that's greater than water, it will want to sink. In this section, we're going to confront this directly and actually figure out, in some cases, for example, for a basketball floating on the surface of the water, how much will be in the water and how much will be out of the water. We'll do an example like that. So starting off with a demonstration, can you float a steel ball in water? The answer is yes, if it's hollow. This hollow steel ball weighs about a quarter of a kilogram. This solid steel ball weighs the same amount. So these two steel balls have the same mass, but obviously the hollow one has much larger volume. Given that the mass density is the mass per unit volume, this solid ball has a much higher density than the hollow one. So, can you float a steel ball in water? And the answer is yes. All right. We'd now like to confront directly what that upward force is on that basketball that you push underwater, because that will allow us to figure out how much of it's going to be out of the water versus inside of the water. And here's how to do it. It's similar to the derivation that we did before with the mass, with the pressure versus depth equation, P2 equals P1 plus rho GH. In fact, we use that equation in doing this derivation. So P2 minus P1 is rho GH. The force, okay, so we're asking about the buoyant force. So this is the force of buoyancy. And we want to know what that is. This whole thing has to be in equilibrium. So the buoyant force is the difference between these two pressure forces. A force P2A that pushes up, like we talked about before, and a force P1A that pushes down. The buoyant force is the difference between these two. And if we factor out an area and we substitute P2 minus P1 as rho GH, then we'll get rho GH times the area here. And we recognize H times area as the volume. So we're going to put a volume in here. So we'll have a rho, we'll have a volume, and we'll have a G. And this rho times the volume is the density of the water, rho, times the volume of the water displaced by this cylinder. It's how much water you've pushed out of the way by putting this cylinder into the water. And so a density times a volume, recall that mass density is a mass per unit volume. And so if we multiply both sides by the volume, we get that the mass is the density times the volume. And so density times volume is the mass of the displaced fluid. Why is it the displaced fluid and not the object? It's because this density refers to the fluid itself, the water. So the buoyant force is the mass of the displaced fluid times G. But if we multiply a mass by G, we get a weight measured in newtons. So this buoyant force is equal to the weight of the displaced fluid. So this is called Archimedes Principle. A fluid applies a buoyant force to an object that is partially or completely immersed in it. And the magnitude of the buoyant force equals the weight of the fluid that the object displaces. So the magnitude of the buoyant force is the weight of the displaced fluid. So up here, if the object is partially out of the water and partially into the water, then the displaced fluid is going to be this. We'll need the weight of this amount of water that's been displaced, pushed out of the way by the box. So let's talk about floating objects, and this is a very important principle for doing a lot of the homework on this chapter. If it's floating and you're not exerting any forces on it, it's just floating, it finds its spot. It's an iceberg in the ocean. It finds where it likes to be, neither too low nor too high, but it finds its nice resting spot. If it's floating, then it's in equilibrium if it's not accelerating upward or downward. And we can say that the sum of the forces in the y direction has to be 0. So what are the forces acting on this floating object? This is the y direction. We've got its own weight acting down, and we've got a buoyant force acting up. So this is its weight, the weight of the object. So this is the weight of the box, not the weight of the water or whatever. That's the weight of the object. If it's floating, then, and if Newton's second law applies, which it does, then that buoyant force has to be equal to mg, because the buoyant force acts up, always acts up, by the way, and mg always acts down. That says that the buoyant force has to be equal to the weight of the object. And that's the statement here. Objects float if their mass densities are less than the density of the surrounding fluid, like we've talked about in a couple of the previous lectures. For floating objects, the magnitude of the buoyant force is equal to the magnitude of the weight of the object. That's this result right here. And this is not, I've not put this in a concept because it's just an application of Newton's second law. But we'll need this one in solving several problems. So the Goodyear Blimp has helium inside of it. It's got a lot of heavy stuff here too. So ultimately, its overall density, if you look at its overall mass and put it on scale and figure out how much what its mass is, divided by its overall volume. So you've got to take into account this heavy stuff down here, the light stuff, the helium inside of the overall volume of everything. That'll be less than air, and therefore it'll float. While helium, that feels that it's less dense than the surrounding air, but the other things will compensate for it, so it can maintain a level altitude if its density is its overall density is equal to the density of the air. If its density were less, then it would rise. If its density were greater, then it would fall. All right. 3 different slides looking at 3 different aspects of this particular problem. You've got a raft made of solid square pine wood. It's 4 meters by 4 meters by 0.3 meters in thickness. So, and the question is whether the raft floats in water, and if so, how much of the raft is beneath the surface of the water. So, we're going to start off with looking at the maximum buoyant force of the object. The maximum buoyant force occurs if it's completely submerged. So that's the case, not what you're seeing right here, but you've got the surface of the water here, and you're putting this entire piece of wood underwater. Okay? Well, in this case, if it's completely submerged, then this buoyant force will reach its maximum value. And how do we calculate it? It's the density of the water times the volume of the water. It's the mass of the water displaced, pushed out of the way by that pine wood. Density of the water, volume of the water displaced times G. Well, density of the water, that's easy. It's 1,000 kilograms per cubic meter. The volume of the water displaced is, or volume of the raft, is given by the length, 4 meters, width, 4 meters, height, 0.3, is 4.8 cubic meters. That goes in here, so that's the volume of the water. And then acceleration of gravity. That's 47,000 newtons is the maximum possible buoyant force if it's submerged. All right. Well, what is the weight of the raft? Well, if that weight is greater than the buoyant force, then, so let me just look at this picture again. Here's the surface of the water. The buoyant force, this maximum buoyant force, is pushing it up, trying to raise it. The weight of the raft, and you say, well, hang on, gravity doesn't act when the raft is underwater. And I say, wrong. Gravity does act. It pulls it down. And if that maximum buoyant force is greater than the weight of the raft, it will float. If the buoyant force is less than the weight of the raft, then the raft will sink. It's exactly, and it works out, you can work it out by just working out the density and comparing the density of the raft to the density of water. What you will find is that the density of the raft, its mass divided by its volume, is going to be less than the density of water. But right now we're thinking about these two forces and thinking about Newton's second law. If that maximum force is greater than the weight, then it's going to float. Well, let's find the weight of the raft. No big deal. What is the weight of the raft? Well, the weight of the raft is the mass of the raft times G, and the mass of the raft is the density of pine times the volume of the raft. So remember, density, rho, is mass per unit volume. So the mass is density times volume, so there's the mass, times G. Well, the density of pine is 550 kilograms per cubic meter. And you say, well, that density is less than the density of water, therefore it better float. And I say, you're absolutely right. That's exact. You can see it that way. This is another way to see the same thing. We're figuring out now the weight of the raft and comparing that with the buoyant force on the raft. So there's the density of pine, here's the volume of the raft, here's G, and that gives us 26,000 newtons as the weight of the raft. Well, that's definitely less than the buoyant force that's holding it up, so the raft floats. So now, to get to the actual question, we're trying to figure out how much of that raft is above the surface of the water. So we know that it's going to float. So if we pushed it all the way underwater, it's completely submerged, it experiences a buoyant force of 47,000 newtons. That buoyant force is greater than the gravity that's trying to pull it down. So the buoyant force raises the raft up, it rises to the surface, and then some of it comes up above the surface, and we want to know how much is above and how much is below the surface. And that's a really cool problem. So if it's floating, and if it's in equilibrium, the argument that we went through before is that there's going to be a buoyant force that's holding it up, and the weight of the raft that's pulling it down. And if those forces are going to balance, then it will be in equilibrium. So that says that the weight of the raft has to be the buoyant force. But the buoyant force now is going to be less. Why? Because less of it is submerged inside the water. And the buoyant force cares about the weight of the water displaced by the raft. So no longer is the raft displacing its entire volume of water, but only a portion of that volume. So we know that, it's 2,600 newtons. We know the weight of the raft is 2,600 newtons. And the buoyant force is going to be the mass density of the water times the volume of the water displaced by the raft times g. Well, what is that volume going to be? It's going to be the volume of this piece here, this volume, shown in blow up right here. Some height h of the raft is below, some thickness of the raft is below the surface of the water. So the volume of that beast is going to be 4 meters by 4 meters by h. So there's the volume of the water displaced. Had it been completely submerged, that h would have been 0.3 meters. So like it was before. I think it was 0.3. Yeah, 0.3. Yeah, right there. So now we have the weight of the raft. We have everything, and the only thing we don't have is exactly the thing that we want, which is how much of it is below the surface. And we just solve this equation for h, and we get 0.17. So about half of it is underwater. 0.17 meters is under, 0.13 meters is above, to add up to 0.3 meters in all. Really, the math is really quite simple. Once you understand these principles and the fact that you've got to give up the idea that there's no gravity acting on that raft when it's underwater. You've got to give up the idea that when a stone is underwater, gravity doesn't act on it. It does. If you've got a stone or a rock in the water, there's definitely gravity acting on it, the same amount of gravity that would act on it if it were out of the water. The only difference is that that effect is lessened by the buoyancy of the water, but the buoyancy of the water isn't enough to overcome the gravitational pull, because gravity is greater in the case of a rock underwater than the buoyant force. A ship floating in the ocean is a familiar sight, but is all that water really necessary? Can an ocean vessel float in the amount of water that a swimming pool contains? And the answer is yes. You could create a channel that just barely fits the ship, and it will still float in that amount of space. Pretty cool. State of charge indicator. Some batteries have these, where you look down this port in the car battery and you see a green dot if it's charged, and a black dot if it isn't. And the way it works is that when a battery is charged, the density of the acid, so this is the acid down in here, this blue, is greater than the density of the green ball. So if this liquid has a greater density than the green ball, then the green ball is going to float. This is a little cage here that restricts the ball to either be down here, up here, or over here. But if the mass density of the battery acid is greater than the ball, then the ball will float to its highest point. And that puts it right in line with viewing down through this port. Whereas discharged battery, the battery acid is less dense than the green ball, and the green dot sinks and moves out of the field of view. So we're looking down through this and just seeing the fluid in here, not seeing the green ball. This is a fun demonstration of Archimedes' principle. It's a principle that shows that the air in our atmosphere here actually exerts a buoyant force on all objects that are walking around, that are on the surface of the Earth. You know that the air exerts a buoyant force because the Goodyear Blimp can stay aloft. So, but this one is I think pretty awesome. This is a demonstration of buoyancy, or Archimedes' principle. What I have here is a hollow sphere made out of brass, it looks like, and a solid cylinder, and they appear, to all intents and purposes, to have the same mass based on this mass scale here. But do they have the same mass? What I'm going to do now is to cover these up with this bell jar. And try and seal the bell jar as well as I can against its base. And then I want to evacuate this jar. Take the air out of it. Okay, as you can see, the two masses are no longer balanced. In fact, it's the hollow sphere that is the heavier of the two. Why? The answer is that when there was air in the chamber, this hollow sphere has a bigger volume and it has a greater buoyancy force. The buoyancy force, the force of the atmosphere pushing up on something, holding it up, is proportional to the mass of the weight. It's equal actually to the weight of the volume of air displaced by the sphere. So this sphere has a much bigger volume, and the volume of air that's displaced by it is bigger than the volume of the mass of the cylinder. So the bottom line here is that this hollow sphere, though it looks like it has the same mass when this is evacuated, or when the air is present, it is actually heavier. And when we then remove, so I'm going to allow air back into this jar. Then these guys appear to have the same mass. But the thing to remember here is that the sphere has a buoyancy force that's partially balancing the downward force of gravity and causing these to appear to have the same mass.